طيب السلام عليكم يا شباب. إن شاء الله today we'll be talking about the Carnot cycle, the application of the Carnot cycle to the heat engine and also the refrigeration and heat pump system. We talked last time that this Carnot cycle is a cycle of reversible processes, and those processes don't have any kind of losses. That's why the process can go in one direction and it can be reversed actually without leaving any trace either on the system or on the surrounding. So that means when we apply the Carnot cycle to a heat engine, I will be calculating the maximum efficiency of this heat engine. Also, when apply it for a refrigeration or heat pump system, that means I'm calculating the maximum coefficient of performance of this refrigeration or heat pump system, as we assume actually we don't have any losses within the system. But in the real situation, actually, we have losses within the system. So that means actually any system, any heat engine should have efficiency that should be less than the Carnot cycle. We cannot reach the Carnot cycle efficiency. And also the Carnot cycle efficiency should be less than 100, below actually 100%. Because if it comes to 100%, that means this is a violation to the second law of thermodynamics. Okay? Like this, also the coefficient of performance should be less than the maximum when calculated using Carnot cycle. And also, in this case, we cannot actually design a refrigeration system without having work input in this case. Okay? So coefficient of performance should be actual value, should be less than the maximum value for calculated based on the Carnot cycle. As we said, Carnot cycle is a reversible cycle. So that means it can go in the direction to convert the heat into work, in the case actually of heat engine, and it can go in the reverse direction, can be reversed and applied for the case of refrigeration and the heat pump system to convert the work into heat in this case. Okay? Type inshallah today we'll be applying this Carnot cycle and see how we can calculate the maximum performance of this system. As I told you, this is actually has an application. So if you have anybody that told you actually we have an air conditioning system or heat engine system that is giving actually this performance, this efficiency for heat engine or this coefficient of performance for a refrigeration system. So how do you know actually this is actually a reasonable value of the performance of this system, either heat engine or refrigeration system? In this case, I have to calculate first the maximum performance using the Carnot cycle, then compare it actually with the actual value that this guy actually is offering. So in this case, the actual value should by any means actually should not exceed the limiting value or the value calculated by the Carnot cycle. And this is a common question for you. I say actually there is a guy, he claims actually that we have, let's say, a heat engine that gives a given efficiency. Is this claim actually true or false? So in this case, I will be calculating the maximum efficiency using the Carnot cycle and compare it actually with the given value. Then actually the given value should be less than the one calculated by the Carnot cycle. Okay, type let's proceed with the Carnot cycle and see how we can apply actually it to a heat engine or refrigeration cycle and how we can calculate the maximum performance of this system. So Carnot reversible cycle. So in this cycle actually all processes are reversible. That means actually this cycle can be applied to the case of heat engines to convert actually the heat. In case of heat engine, to convert the heat into work. And it should be working on a cycle as we said. Also, we can reverse the process to be reversed, to be applied actually to the case of refrigerator and the heat pump system. And in case of refrigerator and heat pump system, it converts actually the work into control of the heat transfer within the system. Okay. In case of refrigeration, what we mean actually we need to absorb the heat either from a food compartment or from air conditioning system. And in case of heat pump, actually like the heat pump is a heating system. In case of air conditioning system, what we need actually is the heat out from the system. So at the end, actually we have to apply work, and in this case we can control the heat transfer within the refrigeration or the heat pump system. But let's say here an example of a heat engine, which is a steam power plant, and see how we can calculate the maximum performance of this system. So if we have a steam power plant, the cycle consists actually of a pump that takes, as we said, it takes the water at low pressure, then actually it raises the pressure of this water. In this case, let's say actually this is section number 1. Before actually this steam, this water is coming into actually this boiler. Then we add heat here We call it actually Q high. We add heat actually to this water to be converted to steam. This water will be converted to steam under high pressure and high temperature, and it will be expanding inside the turbine. Then we can generate shaft power. At the exit of this turbine, it says this is 1, so this is section 2, and this is section 3. We have actually a mixture of saturated liquid plus vapor mixture. Then in this case, we pass it through a condenser. A condenser actually is a heat exchanger in which we have a cooling water. In most of the cases, actually, for a steam power plant, we have cooling water. That is coming actually at low temperature, so it comes here. Then it will actually, this cooling water will absorb the heat. So heat is rejected in this case to the cooling water from the flowing steam. So we call it Q low because heat is rejected at the low temperature. Then in this case, this saturated mixture of steam will be converted back to water at state number 4. Then actually this cycle is repeated again, okay, to generate a continuous work out of this cycle. So let's assume actually we are applying Carnot cycle on this heat engine. To have a Carnot cycle, let's look at the process from 1 to 2, which is actually a heat addition process. We said the only way to have actually a reversible process, to have a reversible heat addition process from state 1 to state 2, that means actually this heat should be added actually under constant temperature. Because we said whenever we have temperature difference, then actually the heat will be transferred from the high temperature to the low temperature. But we cannot reverse this process because the heat cannot be transferred from low temperature to high temperature. So that means the only way to have this process from 1 to 2 reversible, that means this heat added should be added under constant temperature. T high equal to constant in this case. I don't know if it is clear or not. So T high in this case should equal to constant. And in this case, we can reverse this process. Okay? Actually, this process, we said we cannot add heat without temperature rise unless we have phase change. That means actually we have saturated water is converted actually from saturated liquid at state 1 to saturated vapor at state 2. And that means actually heat is added in this case under constant temperature while having phase change in this case. So process from 1 to 2. So process from 1 to 2. We call it actually isothermal heat addition process. That's why we can have this process actually reversible. And this process is done at constant temperature. T high is equal to constant in this case. But let's look at the expansion process through the turbine. In order to have this process actually reversible, that means we should not have any kind of losses. So in this case, we should not have heat lost from the system. The system should be adiabatic. This turbine should be adiabatic. If we have heat is lost to the surroundings, that means we have temperature difference. So we can reverse the process. So in order to have this process from 2 to 3 reversible, either expansion or in compression, then in this case we should not have heat losses. And also to have this process reversible, we should not have friction. Friction should equal to 0 in this case. But what does it mean if we have adiabatic? We don't have in this case temperature difference, and we don't have friction. That means we don't have heat losses in terms of friction, which at the end convert into heat and the higher activity of the molecules. So adiabatic frictionless means actually that the entropy is constant while the expansion process from state 2 to state 1, state 2 to state 6. So we have the process from 2 to 3. To have this process actually reversible, we have to have the system is adiabatic turbine and also it should be frictionless. Adiabatic frictionless means isentropic. So this process is called as isentropic expansion process. So in this case, the entropy is equal to constant for the process from 2 to 3. Okay. But for the heat rejection process from 3 to 4, in this case, actually to have actually a reversible heat rejection process, this heat also should be rejected at constant temperature. T low also should be constant in order actually to have this process reversible. That means we are converting here steam from saturated vapor to a saturated liquid. So we have phase change from the saturated vapor to the saturated liquid. So in this case, actually heat is rejected, but this is latent heat. but actually the temperature will be remaining constant, and we will have phase change from saturated vapor to saturated liquid. So the process, let's say from 3 to 4, this process actually is isothermal heat rejection process. Isothermal heat rejection. T low should be constant in order to have this process reversible in both directions in this case. And also for the process here for the pump, we have work input to this pump. And in order to have this process from 4 to 1 reversible, it should also be adiabatic. We should not have heat is lost. And also we should have actually the friction should equal to 0 in this case. Adiabatic and the frictionless, that mean also the process for compression inside the pump should be also isentropic. So the process from actually 4 to 1, this process actually is isentropic compression process. So this isentropic compression, also the entropy would be constant in this case. Okay. Inshallah, we will be talking in chapter 7 about the isentropic relation, how we can relate the properties at state 1 with the properties at state 4. Like this, also the properties at 2 with the properties at 3. We will see inshallah the isentropic relation. We will have actually T3 over T2 will equal to B3 over B2 to the power K minus 1 over K. I will give you, and inshallah in chapter 7 I will be talking about actually more details about the isentropic relation. So if you have the condition here before actually this steam turbine and the condition after the steam turbine, then in this case we can assume the process for a reversible process is isentropic. Then in this case we can proceed actually with the solution to calculate the work out of this system. Okay, so let's say he give you the pressure at the outlet, and here the process is isentropic. That means the entropy at the outlet is the same as the entropy at the inlet. So we have two properties at the exit, then we can calculate actually the enthalpy, and then we can apply the first law of thermodynamics even for this turbine to calculate the work out of this turbine. Okay, but to evaluate the performance of this cycle, in this case we calculate actually the thermal efficiency. Okay, so to evaluate the performance, we calculate the thermal efficiency of this system. Thermal efficiency is equal to the net work, as we said, the net work divided by the heat element. So heat thermal for this cycle, the actual value should equal to work net divided by Q high. The work out, which is the net work, the difference between the turbine work and the pump work, divided by the heat added in this case. What we said, work net is the same as actually Q net divided by Q high, and the Q net is Q high minus Q low divided by Q high, and that should equal to 1 minus Q low divided by Q high. Okay, and this is the actual efficiency of this engine. But if we are applying actually a Carnot cycle, in this case we can calculate the maximum. If this cycle actually is operating on the Carnot cycle, in this case the efficiency should be the maximum efficiency of this cycle. And we call the efficiency in this case eta thermal reversible. We call it reversible, or we call it the maximum in this case. And it is the same, equal to work net divided by Q high. But in order to have this efficiency maximum, that means actually the net work in this case is maximum. And also the heat input in this case should be minimum. So if he asks you in any application, calculate the thermal efficiency of this engine for minimum heat input to the system. Minimum heat input, that means the efficiency is maximum and the system is working on Carnot cycle. But if he asks you to calculate the maximum efficiency, the efficiency of the system for maximum work out of this system. Maximum work out, that means the system is working on a Carnot cycle in this case. Okay, and that should equal to 1 minus, as we said, Q low divided by Q high. But in case actually of Carnot reversible cycle, heat is added under constant temperature, and heat is rejected under constant temperature. That means actually heat is a sole function actually of temperature. And we can prove that actually the ratio between Q high over Q low for the Carnot reversible cycle, Q high over Q low reversible, that is the same ratio as T high divided by T low. But this is only applied for the reversible process, for the Carnot cycle. Because heat is added under constant temperature and rejected under constant temperature, that means the heat is only a function of the temperature. That means Q high over Q low is the same as T high over TO in case when we have a reversible process. I will prove you this relation inshallah for you, but based on this shabab, we can calculate the maximum efficiency in this case will equal to what? 1 minus Q low over Q high. Q low over Q high for the Carnot cycle is the same as T low over T high. And this is actually, this is the maximum performance of the system, and this is the actual performance. Okay, so we cannot substitute Q low over Q high as T low over T high unless the system is working on a Carnot cycle. And the maximum efficiency or the reversible efficiency is working at maximum divided by Q high minimum, which is 1 minus Q low over Q high. Q low over Q high for a reversible process is the same as T low over T high. So this is the maximum performance of the engine. If I have T low and T high, then I can calculate the maximum efficiency. And then I can compare it with the actual value, which is working it divided by Q high in this case. Okay. In some cases, if the case is very simple, but it is not that easy. So in some cases, he will not give you, in this case, the value of the heat added or heat rejected directly, and they may not give you actually the work of the turbine as well. So what should we do in this case? So in some applications, let's say this is step number 2, as we say. In some cases, actually, he may give you, this is a steam power plant. They can give you actually the pressure B1 at the inlet, pressure B1 and temperature T1. Then we can calculate the installed BH1 at the end. Okay, and out of this boiler, I can give you pressure B2, temperature T2. Then using a steam table, I can calculate installed BH2. But can we actually consider this boiler as actually a steady flow open system, device single stream? And then we can apply the first law of thermodynamics to calculate Q high. We said Q dot minus work dot equal to M dot multiplied by delta H plus a change in kinetic plus a change in potential, which are neglected. Okay. For this boiler, actually, we don't have work. Okay. So that means the heat transfer will equal to M dot multiplied by delta H. So Q dot high will equal to the mass flow rate of steam, M dot multiplied by what? The enthalpy H2 minus H1. So in some cases, he may give you a steam power plant, and he give you the condition at the inlet of the boiler and the condition of steam at the outlet of this boiler. Then we can apply the first law of thermodynamics. For this boiler, we have a steady flow open system. At 1, flow is coming at 1 and leaving at 2. Then we can say Q dot high will equal to M dot steam multiplied by H2 minus H1. Like this also, if we apply the first law of thermodynamics for this turbine to calculate the work in this case, then in this case we will say the work of the turbine will equal to the mass flow rate of steam multiplied by H2 minus H3. Okay, and this is actually the net work out of this turbine. Like this also, we can calculate Q dot low if we apply the first law of thermodynamics will equal to M dot multiplied by H4 minus H3. And we can give you the condition of steam at step number 3 and at step number 4. Then we can calculate H3 and H4 multiplied by M dot. Then we can calculate Q dot low as well. And in some cases also, Shawad, he may give you the condition instead of steam at state 3 and state 4. He may give you the condition of the cooling water. Let's say we have a cooling water coming in at state A here, and here actually it is leaving at state B. Okay, I can give you the condition for A and B. Then we can say Q dot low, which is the heat absorbed by the cooling water. It should be the same as heat rejected from steam, from state 3 to state 4. This is a heat exchanger. Okay, so the heat absorbed by the cooling water equal to the heat rejected by the hot stream from state 3 to state 4. So Q dot low can equal to M dot cooling water multiplied by delta H, which is HA minus HB. Okay, this is actually HA minus HB This is a cooling water. We can get, if pressure and temperature are given, then we can go to steam table, calculate HA and HB, then we can calculate Q dot low. If not, if temperatures only are given, TA and TB, then we can consider the cooling water as liquid in this case, and we can consider the specific heat analysis to calculate delta H, thermo dot cooling water. Delta H will equal to CB of the cooling water multiplied by TA minus TB. And this is Q dot low. And CB of cooling water is calculated from table SQ. Okay? I hope that should be clear-ish then. So if we apply the Carnot cycle, then in this case, the efficiency will equal to work net over Q high or 1 minus Q low over Q high. But in some application, he will not give you the value of Q low or Q high directly. So he may give you the condition at the inlet and the outlet of the boiler, then we can calculate Q dot high, the condition of water using steam table. Also, we can calculate the work of the turbine by knowing the condition at the inlet and the outlet of this turbine. And also for the heat rejected in the condenser, he either give you the condition of steam at state 3 and state 4, then we can say Q low will equal to M dot multiplied by delta H, and then we can calculate the properties of steam from the steam table. Or he can give you the condition of the cooling water. The heat rejected by steam is equal to the heat added to the cooling water. We can consider it M dot cooling water multiplied by the enthalpy difference. This enthalpy difference, we can consider it CB multiplied by delta T as well. Okay. So this is for the case of heat engine. When we apply the Carnot cycle for a heat engine to convert the heat into work. And we can apply this cycle as well for the refrigeration and the heat pump cycle. And in this case, we'll be converting actually the work into heat in this case. Okay. But let's see how we can apply this and how we can calculate actually the maximum coefficient of performance in this case. Okay. So for the case of refrigeration and the heat pump system, so let's represent here the refrigeration cycle. In the refrigeration cycle, let's say we have here actually the refrigerant. 134 is recirculating inside this cycle. Let's say actually this is step number 1. We will pass actually this refrigerant inside an expansion valve. So here we have expansion valve or throttling valve from state 1 to state 2. So in this case, steam will be converted actually from liquid at high temperature and high pressure to liquid at low temperature and low pressure. Then in this case, we can pass it inside the evaporator, which is a food compartment in case of refrigeration system, or in case of air conditioning, it is actually we pass the area actually here around the evaporator so that actually can absorb it. So in this case, heat is added Q low under low temperature to the system. So in this case, the freon will be converted from state 2 to state 3. From liquid, it will be converted to vapor at state 3. Then in this case, we have compressor from state 3 up to state 4. It will compress actually this freon onto high pressure and also high temperature. Then we pass actually this freon inside the condenser, which is actually the set of hot wire in the back of the fridge. You can look at it at your home. Then in this case, heat will be rejected at high temperature to the surrounding air. And this freon will be converted actually from state 4 to state 4.1. State 4 actually is saturated vapor, steam. It will be converted to saturated liquid. But this saturated liquid is still at high pressure and high temperature, so we pass it inside an expansion valve or throttling valve to reduce its temperature. And also we reduce its pressure. Then in this case, it can be passed inside the evaporator to absorb the heat either from the flowing air around, in case of air conditioning system, or actually from the food compartment. So here heat is added at low temperature and rejected in the condenser at high temperature in case of the refrigeration cycle. In case of heat pump, what we need from the system is Q high, like actually using the air conditioning system as a heating system. We just flip it to have the condenser inside, then we will have Q high inside. Okay. So we absorb the heat from outside and reject it inside in this case. Okay. So the difference between refrigeration and heat pump is what we need from the system. but actually it is the same system. Air conditioning system, so we need Q low. We needed heat pump, then we need Q high in this case. So let's consider actually Carnot cycle in this case. To have this process actually from 4 to 1 as a reversible process, that means actually this Q high should be added under constant temperature. And we should have phase change actually from vapor phase to the liquid phase in this case. And also to have heat rejected here, a reversible process, heat should be rejected under constant low temperature also in this case. Then we can have actually this process reversible. Also, this expansion process in the expansion valve should be adiabatic, and also it should be frictionless. Adiabatic frictionless, that means actually the entropy in this case should be constant in this case. And in case of compressor, we have work input to the compressor from state 3 to state 4. It should be also adiabatic and it should be frictionless. So the process here, the compression process also should be under constant entropy in this case. But the cycle شباب is reversed. Instead of going to convert the heat into work in case of heat engine, in this case, and going in this direction, convert the heat, add heat at high temperature, reject heat at low temperature, then we can have work out in case of heat engine. And the cycle is proceeding clockwise. In case of refrigeration system, the cycle is actually proceeding counterclockwise. And in this case, we have work input, and then we have the outcome actually is heat transfer in this case. Okay. So actually, it is the same cycle, but the cycle has been reversed in this case. Okay. So in this case, the coefficient of performance of the refrigerator, what we need from the system is Q low divided actually by the work net of the system. And we said the system is working on a cycle, so Q net is the same actually as work net, so it's equal to Q low divided by Q high minus Q low in this case. Okay, this is the coefficient of performance. But what about the maximum one or the reversible one using the Carnot cycle? The coefficient of performance of the refrigerator, reversible or maximum. So it is the same, equal to Q low divided by working. But in this case, this Q low should be the maximum value. So if he asks you to calculate the heat actually absorbed inside the evaporator, to calculate the coefficient of performance of a refrigeration system for a maximum heat absorbed inside the refrigerator. That means actually if Q low absorbed is maximum, that means the system is working on Carnot cycle in this case. And also it is the same when we ask actually for minimum work input to the system. As a matter of fact, شباب, Carnot cycle is a reversible cycle. So it produces actually the maximum and it consumes actually the least in this case. So if he said we need the least work or the minimum work to the system, calculate the coefficient of performance of the refrigerator for minimum work input, that means actually the system is working on a Carnot cycle and the coefficient of performance is maximum in this case. Okay, and that should equal to Q low divided by Q high minus Q low. Divided by Q low, up and down, so it will equal to 1 divided by Q high over Q low minus 1. Then we can equate it, then we can get it actually in this form. But we said in case of reversible system, the ratio Q high over Q low is the same as actually T high over T low in case when we have a reversible heat engine working on Carnot cycle, because heat is added at constant temperature and heat is rejected at constant temperature. That means heat is only function of the temperature. So the ratio of heat transfer is the same as the ratio of the temperature in this case. So that means we can just substitute it here, Q high over Q low, T high over T low. That should equal to T low divided by T high minus T low. And this is the maximum coefficient of performance of the system, and that should be the actual value. So this is actual for a refrigeration system, the actual value, and that should be actually the maximum value. Okay, calculated based on the Carnot cycle in this case. Okay, but this is in case of a refrigeration system. But what about the heat pump? Heat pump is just the reverse. If the system is working on a heat pump, what we need from the system is Q high in this case. So the coefficient of performance, in this case, in case of heat pump, what we need from the system is Q high divided by the net work input to this system. So equal to Q high divided by Q high minus Q low in this case. Type the maximum coefficient of performance of heat pump reversible, or we call it maximum, on Carnot cycle based on the Carnot cycle. That should equal to Q high maximum divided by actually work in it minimum in this case. And it is the same as Q high divided by Q high minus Q low. If you divide actually by Q high up and down, and we apply this relation for reversible Carnot cycle, then this should equal to T high divided by T high minus T low. And this is the maximum performance, and this is the actual performance of a heat pump in this case. Okay. طيب, let's represent this cycle on the TS and also on the PV diagram for the heat pump and also for the refrigeration cycle. Okay. So it is the same, but just we reverse the direction of the cycle. Instead of converting heat into work in the heat engine, we convert the work into heat in case of refrigeration cycle. So if you look in the case of heat engine, if we represent this process on the TS diagram, process from 1 to 2, which is the heat added actually in the boiler, heat is added in this case, Q high, and the T high equal to constant for the process from 1 to 2. Process from 2 to 3, which is the expansion in the turbine to have work out 2 to 3, and this process should be actually isentropic expansion. 3 to 4, which is actually heat, is rejected at low temperature, and the T low equal to constant in this case. So 3 to 4 is the heat rejection in the condenser. Then we can have the process from 4 to 1, work is added inside the pump, and in this case, this process is also isentropic. The entropy in this case should be constant in this case. Okay. Usually, you have the area contained on the TS diagram by a cycle. This represents actually the net heat transfer to the system. And as the system is working on a cycle, work is the same as Q. Inshallah, in chapter 7, we'll have the relation between heat transfer and the entropy. We'll have delta Q is equal to TDS, or we can say Q is equal to integration of TDS. So that means the heat transfer should equal to the area under the curve on the temperature entropy diagram. Okay? So this is in case of heat engine. Also, we can represent this process on the pressure volume diagram. So process from 1 to 2, this is actually the heat added under high temperature, under constant temperature. 2 to 3 actually is the isentropic expansion process. From 3 to 4 is actually the heat rejection, here is the work output. And process from 4 to 1, actually this is the work input inside the pump, and it should be isentropic actually compression process from 4 to 1. It is very important to know actually the representation on the TS and PV diagram, so that actually you can link state 1 to state 2. T1 is the same as T2, which is T high. And from 2 to 3, the entropy is the same. S2 is the same as S3. 3 to 4, T3 is the same as T4. 4 to 1, S4 is the same as S1, the entropy in this case. Inshallah, here is the slide. We may give you in the exam of something like this. I can give you the condition at state number 1, and then we can proceed from state 1 to 2 to 3 to 4 until we get back to the initial state in this case. And then we can calculate Q high, Q low, work net, and all of these properties in this case. This cycle, the Carnot cycle, can be applied for heat engine and refrigeration cycle, for open system and for closed system. As I told you, in case of heat pump cycle, in case of heat engine cycle, here is the cycle. This is for a heat engine. We said heat is added here. I can give you actually the condition at the inlet and the outlet, then we can calculate Q high. But we apply actually the first law of thermodynamics for a steady flow open system device in this case. For all of these cases, to calculate the heat transfer, work, heat transfer and also the work for this pump. We take one device, apply the first law of thermodynamics for open systems, then we can calculate the heat transfer. This is actually applied for open systems. The cycle also, Carnot cycle can be applied for the case of closed system when we have a gas in a piston cylinder device. So that means gas in a piston cylinder device, the system is closed. So if we consider this process expansion, let's say heat addition from state 1 to state number 2, this heat addition actually is isothermal. So the temperature T1 is the same as T2. But if I want to calculate the heat transfer for this closed system, I will not say Q dot equal to M dot delta H. This is not an open system like the boiler. It is actually a closed system. So I will apply for process from 1 to 2, Q from 1 to 2 minus 4 is equal to delta U. So we don't have work, so the heat transfer will equal to delta U, which is M multiplied by U2 minus U1. So the cycle can be applied either for open system component, like the steam power plant, we have boiler, turbine, condenser, all of these open system devices. Or it can be applied for a closed system cycle, like when we have internal combustion engine. We have a piston cylinder device, and we burn the fuel and the gas. Then we can have expansion process. This is typically the engine in your car. So in this case, the process of heat addition, we consider it a closed system. So instead of saying Q dot will equal to M dot delta H, like the case of boiler, it will be Q minus work equal to delta U. Okay. I will solve some examples with you, inshallah, and I will show you how we can calculate, apply this Carnot cycle to a closed or open system devices. Okay. But this is the representation for the heat engine. For the refrigeration cycle, we can represent the process also in the TS diagram. From state 1 to state 2, which is actually the isentropic expansion in the expansion valve. This is the entropy is constant. From 2 to 3, this is actually heat is added at low temperature under constant temperature in the evaporator. Then we have the work input in the compressor from state 3 to state number 4. Then from 4 to 1, heat is rejected at high temperature at Q high in this case. Okay, and the area contained by this cycle on the TS diagram represents the heat transfer Q net, which is the same as work. So the area on the PV diagram here, this area represents the work. Work is equal to integration of PTV. That means the work is equal to the area contained by this cycle on the PV diagram. This is the working, and it should be the same also as Q net, as the system is working on a cycle. Okay, we can represent this process also on the pressure specific volume diagram. So from state 1 to state 2, this is actually not this one. From state 1 to state 2, this is the isentropic expansion process in the expansion valve. From 2 to 3, this is actually the heat addition, heat added at low temperature. From 3 to 4, actually, this is the work input through the compressor. And from 4 to 1, this is the heat rejected Q high under high temperature. And the area contained by the cycle represent in this case the network of the cycle in this case. Okay. That's all about the application of the Carnot cycle for a refrigeration heat pump system, and also for the case of heat engine for the case of heat engine system in this case. And we have learned how we can calculate the maximum efficiency for the case of heat engine, and also how to calculate the maximum coefficient of performance for the case of refrigeration and also for the case of heat pump system. And we have represented also today the process on the TS diagram and the process on the PV diagram, and we see the relation how we can proceed from state 1 up to state 4. This is for the heat engine, and also we have represented this for the case of refrigeration and the heat pump system in this case. Okay, I told you in case of reversible system, the ratio Q high over Q low in case of Carnot cycle is the same as T high over T low. So inshallah next time I will give you this proof, how we actually prove that Q high over Q low is the same as T high over T low in case of Carnot heat engine. So inshallah we'll be talking about this. So this is what we said. This is the maximum efficiency. So the maximum thermal efficiency for actual heat engine, irreversible engine, it should be less than the maximum value. But if the system is working on a Carnot cycle, we say this is a reversible heat engine. So the efficiency is equal to the reversible or the maximum efficiency. But can we have efficiency that is greater than actually the thermal, the maximum value by Carnot cycle? No, this is an impossible case. We cannot have a system that have efficiency that is greater than the efficiency calculated based on the Carnot cycle, which is the maximum efficiency equal to 1 minus the low temperature divided by the high temperature in this case. Like this also for the case of refrigeration and heat pump system, we cannot have coefficient of performance greater than the maximum value calculated by Carnot cycle. If it is equal to the maximum, this is the case of reversible Carnot cycle, and it should be actually for the actual or irreversible cycle, any system should have coefficient of performance that is less than the maximum value calculated using the Carnot cycle. Okay, so inshallah next time I will give you some example and show you how we can calculate the maximum performance of the system. Assalamu alaikum.